In this section, we're going to look at Mpeg audio compression, and I think we should be able to appreciate the complexity in Mpeg compression method after this. There are many strategies used, such as the psychoacoustic model, which make use of frequency masking, temporal masking, and in this method, a large multi-dimensional lookup table is constructed to transmit mask frequency components using fewer bits. So generally, how this is done is first, a filter bank is applied to the input signal and break the input signal into its frequency components. And then at the same time, there's a psychoacoustic models applied to the same signal for bit allocation block. And then from there, the number of bits allocated are used to quantize the information from the filter bank that we did in the first step, and hence this would give a compression of the audio file. So Mpeg audio offers 3 compatible layers, layer 1, 2, 3, and Mpeg standards actually represents 3 different aspects of multimedia: video, audio, and system. So Mpeg audio is form the portion of the audio component. So Mpeg offers 3 compatible layers, layer 1, layer 2, layer 3. Each of the layer able to understand the lower layer, or we call it as downward compatible. Each succeeding layer offers more complexity in the psychoacoustic model, and hence it offers better compression for a given level of audio quality. So basically, layer 3 would be more complex than layer 2. Layer 2 is more complex than layer 1. So however, this increase in complexity would increase the delay in processing as well. So the objective of Mpeg layers is a good trade-off between quality of the audio and also the bit rate of the audio. So we want to balance in Mpeg. We want to get the balance of the quality and the bit rate. So what does layer 1, layer 2, and layer 3 does? Layer 1 quality is considered quite good. So digital audio tape, DAT, typically use layer 1 at about 192 kilobits per second. And then layer 2 provides more complexity, and it is widely used in digital audio broadcasting. And layer 3 is the most complex, which is the MP3 format, and is however, most of the complexity is at the encoder rather than at the decoder side. So this makes the MP3 player is more popular. So these are the strategy in Mpeg audio compression. So the strategy used in Mpeg audio compression relies on quantization and human auditory system. So as previously stated, we cannot really differentiate, as a human ear cannot really differentiate the sound within one critical band in terms of perceived loudness and mask frequency. So Mpeg make use of these attributes in the psychoacoustic model of the Mpeg audio compression. So the Mpeg encoder make use of a bank of filter the filter would analyze the spectrum of frequency or the range of frequency components of the audio signal by calculating the frequency transform. So, and then the bank of filter decompose the signal into subbands. So parts of the Mpeg encoder we have layer 1, layer 2 and layer 3. So layer 1 and layer 2 codec use a filter called quadrature mirror filter bank, and layer 3 codec adds DCT or discrete cosine transform and psychoacoustic model such as Fourier transform. Okay, so we're gonna look at this in more detail later. So after that, frequency masking is used by using psychoacoustic model to estimate the just noticeable noise level. In quantization and coding stage, the encoder balance the masking behavior and the available number of bits. For example, samples that are determined by the psychoacoustic model as not so important or difficult to be perceived by human ear are allocated with very few or no bits at all, while samples that are perceived the most by human ear are allocated with more bits. So frequency masking happens within the same critical band, right? And we have learned that the bandwidth of each band is not equal. It's non-uniform. However, in Mpeg, to keep the design simple, the model adopts a uniform width of all frequency width. So all the frequency analysis filter would have a uniform width using 32 overlapping subbands. So let's look at in general what does Mpeg layer 1 does, and Mpeg layer 1 encoder, Mpeg layer 2 encoder, and Mpeg layer 3 encoder does. So for Mpeg layer 1, the psychoacoustic model use only frequency masking with bit rates 32 kilobits per second for mono channel and 448 kilobits per second for stereo channel. In layer 2, another psychoacoustic model is adopted, which is temporal masking, as we learned before, by accumulating more samples and examine the temporal masking between the current block of samples and the one just before and just after. So the current, the previous one, and the next one is blocked together in order to examine the temporal masking. So the bit rate now is 32 to 192 kilobit per second for mono channel and 64 to 384 kilobits per second for stereo channel. And then for Mpeg layer 3, Mpeg 1 layer 3, lower bit rates is applied by using more sophisticated subband analysis with non-uniform subband width. Also, non-uniform quantization and entropy coding such as Huffman is added. Huffman coding is added in layer 3 encoder. So this is the overall algorithm for encoder and decoder of Mpeg audio compression method. So if we look at the Mpeg audio encoder here, okay, so we have the input will be the audio signal, the PCM input, PCM audio input, and then the first one is that the audio signal is mapped into frequency domain, and then also by using the same audio signal, the psychoacoustic model is applied. The output of the acoustic model will determine what signals to be kept and what signals to be discarded, and this would feed into the bit allocation algorithm. So the signal is quantized and the number of bits is determined in this block. After that, bit stream formatting is as the end step. We'll add any other extra information to the bits, and the signal is encoded in continuous bit stream. So the basic algorithm is that the input to the Mpeg encoder is divided into 32 frequency subbands via a filter bank. So there's a linear operation that takes 32 PCM audio samples and sample in time, and the output of this would be the output of the filter would be 32 frequency coefficients. And the layer 1 encoder, the set of 32 PCM values are first assembled into a set of 12. So for every subband filter, so there are 32 subband filter, and each subband filter will output 12 samples. So accumulate we would have this will accumulate to 384 samples. So let's look at this figure. It shows the layer 1, layer 2, and layer 3, the difference of layer 1, layer 2, and layer 3 codec. This is how the audio PCM inputs are mapped into the frequency domain, which is by using the 32 subband filters. Here, 32 samples are input into each subband and produce one sample output according to the frequency subbands in each filter. So here, if we are using layer 1 encoder, then there are 12 samples are assembled in each frame. So this would cause a bit of a time lag in order to accumulate 12 samples, and we also have 32 subbands, so this makes 384 samples per frame. So the output of each subband would be 12 would be one sample, but before it goes to the next processing, 12 samples is accumulated to form one frame for layer 1 codec. But if you are using if that audio is encoded with layer 2 or layer 3 encoder, more samples are accumulated for each frame, because like we said earlier, we need more samples to apply the temporal masking. So for layer 2 and layer 3, each frame there are 3 groups of 12 samples. So for each subband there are 36 samples accumulated. Thus at the end, for one frame of layer 2 and layer 3 encoder, there would be a total of 1152 samples, because we have 36 samples for each subband and we have 32 subbands in total. Moving on to the next step is bit allocation algorithm. So the bit allocation algorithm is not part of the Mpeg standard. Thus, it can be done in many possible ways, but the goal is to ensure that all of the quantization noise is below the masking threshold, so that quantization noise that can produce distortion would be inaudible to our human ear. So how to do this? So this is one common scheme. For layer 1 and layer 2, the bit allocation process starts by computing the mask to noise ratio, MNR, for each subband. So MNR is calculated. First, the psychoacoustic model provides the signal to mask ratio, SMR, and the SNR, signal to noise ratio, is given as a function of bit allocation tables provided in the standard. So the algorithm finds the subband. So after calculating the MNR, mask to noise ratio, the algorithm would find the subband with the lowest MNR, whose bit allocation has not reached the maximum limit. So the bit allocation for that subband with the lowest MNR is increased by one level, and the number of additional bits required is subtracted from the total number of bits available. So now with the new bit allocation for the subbands, the SNR will be improved, right? Because SNR depends on number of bits. Hence, the MNR would improve as well. Now, the subband with lowest MNR is searched again, and the bit allocation process is repeated. Then we take another bit allocation from the total number of bits available. And this process is repeated until all the available bits are used. So, at the end of this process, subbands that are determined by the psychoacoustic model as not so important or difficult to be perceived by human ear are allocated with very few bits, while subbands that are perceived the most by human ear are allocated with more bits. So mask calculation and subband filtering that we discussed just now are done in parallel. The masking curve calculation requires an accurate frequency decomposition of the input signals, which is a frequency mapping, frequency domain mapping, and this can be done by using DFT, discrete Fourier transform. So this is the block diagram for Mpeg 1 layer 1 and Mpeg 1 layer 2 audio compression. So you can see here the frequency domain mapping is done by using the filter bank with 32 subbands, and the same input goes through the psychoacoustic model before it is encoded with the linear quantization. So for layer 1, there are 16 uniform quantizers pre-calculated. So we need 4 bits. However, so to represent 16 uniform quantizer, we need 4 bits. Because to the power of 4 is 16. But the maximum resolution is only 15 levels, because one of the level is sent as a site information for each subband. So the main difference of layer 1 and layer 2 implementation, as we can see before in the diagram, layer 1 use 12 samples are encoded in each frame for each subband, while for layer 2, 3 groups of 12 samples are used. So making 36 samples for each subband, and in total of 1152 samples per frame. Another enhancement in layer 2 is temporal masking is applied, as well as frequency masking. By having more samples, both psychoacoustic model of temporal and frequency masking can perform better with the longer time window. So now since we have 36 samples as output of each subband, so the bit allocation would need to be increased as well for this. This one is the Mpeg 1 layer 3 or the MP3 format. So for MP3 format, multiple enhancements are added. The filter bank used in Mpeg layer 3 is a hybrid filter bank which consists of polyphase filter bank and MDCT, modified discrete cosine transform. The quantized value now are coded with Huffman coding as a specific method for entropy coding, and Huffman coding is lossless. So this is the overall algorithm for Mpeg audio layer 3 coding. So MP3 Mpeg or Mpeg 1 layer 3 is a 1 or 2 channel perceptual audio coder that provides excellent compression of music signals. Compared to layer 1 and layer 2, it provides higher compression efficiency. For example, it can typically compress high quality audio CD data by a factor of 12 to 1 and still maintaining the CD the high audio quality. So in general, MP3 is appropriate for applications either for storage or transmission, either mono or stereo channel. Here are other codecs with their bit rate range. Other audio codecs technologies are Dolby, and you must have heard about Dolby Digital in Sony Attract. So common audio codecs used with HDTV is Dolby AC3. Providers such as Astro and Netflix supports Dolby Audio as well. Okay, so let's look at a little bit about Dolby. Dolby Digital is the first audio decoding technology before Dolby Atmos is commonly used in movie theater. So the idea is to provide a surround sound to the user, or we call it as virtual surround. So there's a few setup in order to have the surround sound. So before that, Dolby Digital is also a lossy format because we want to fit the audio with this format in this or transmitted or broadcast digitally through cable or satellite. So these are among the setups of speakers in order to give us the surround sound experience: 5.1, 7.1 and 9.1. So 5.1 means we have 5 speakers and 1 subwoofer. So here's the 5 speakers. So 5.1 means we have 5 speakers and 1 subwoofer. And then 7.1 setup means we add 2 more speakers on the left and the right, adding another dimension to the surround sound. 9.1 we add 2 more speakers to the front. With Dolby Atmos, there is 5.1.2 setup. So the 0.2 means we are adding 2 height speakers. Means in total of 7 speakers or 7 channels altogether. The height speakers or ceiling speakers would give the sound of the things that goes above us, such as airplanes or raining sound maybe. So ultimately all these setups is to give us the best experience with the surround sound.